corrected last page is there. All right, so now we're going to dive into territory that would have applied to the other final project that I have historically assigned. So over the next couple lectures, you can decide for yourself if you are happy or not that I chose the bicycle crank arm for you guys. So this is, we're going to apply the buckling concept that we talked about analytically before break, and then wrapped that up on Monday. And we're going to apply the finite element method. So using matrix solutions, how do we account for buckling? So we're going back to this polynomial equation, right, to represent beam deflection in matrix form. And for a beam that doesn't have transverse loads, but has a applied axial force, that buckled shape, all right, will be something like this. And so that deflection, all right, is represented by this expression. So our goal is to find the critical buckling load using the finite element method. And to do that, as before, we have to consider the change in geometry due to the applied loading. So if we zoom in on, all right, we'll just kind of zoom in on this end here and take a finite length of the beam, call that dx. The displaced position of, we'll just say the top fiber, right, would be something like this. And then this distance, we'll call that dv. Where this is ds. And then that angle is dv over dx. Right, using small angle theory. Let's see, I'm going to rewrite that. I'm going to call that theta, or actually I'm going to call that phi. Let's see. What's the least confusing here? Yeah, I'm just going to call that alpha. That's what I'll do. I'll call that alpha because I don't want to confuse it with the thetas because this is a general alpha. All right, so we'll say alpha is equal to dv dx thanks to small angle theory. All right, so we can apply geometry and say that ds squared is equal to dx squared plus dv dx times dx, or just dv squared. And after a very long derivation, that would lead to ds minus dx, which represents the change in length of that small portion, is equal to 1/2 times, in parentheses, dv dx squared times dx. And this is going to be a shortening of the beam due to a compressive axial load. All right, so this is a very long derivation. We're going to skip it. All right, so now that we have defined that, all right, change in element length due to bending, we're going to go back to virtual work, right, and define the increment of work done according to this expression here, and then set the increment of internal strain energy equal to the increment of work done, and then apply equilibrium. So this, if you recall from our previous finite element analyses, right, when we plug in v of x into these expressions, we end up with this equation for beam bending, right? And now with this new relationship here, right, we also will end up with this matrix, which we call the stability matrix. So for short, I'm using the capital L to represent the stability matrix. And the right-hand side is all zeros because there are no transverse loads or moments applied to this beam. All right, so we're just looking at a single element, node 1 on the left, node 2 on the right. And if we apply our boundary conditions with a pin support on the left and a roller on the right, that means our displacements at nodes 1 and 2 will be 0, but the rotations we don't know. So with the displacements being 0, that would eliminate the first and third columns in these matrices. All right, and I'll go ahead and I'll label this according to what we already know. It's capital K, the stiffness matrix. Now, because the right side is all zeros and because the load P is unknown, that's what we're trying to solve for, this is an eigenvalue and eigenvector problem. And that's something we already knew from our previous lecture with the analytical approach. But those are the two criteria for this type of equation. So say since right-hand side, which represents applied external transverse forces and moments. All right, so then after applying those boundary conditions, we're left with a 2x2 first partition. And then if we divide by EI over L cubed, that ends up as first matrix is 4, 2, 2, 4 times theta 1L and theta 2L. So that's our beam stiffness matrix minus, we'll have in front of the stability matrix, it'll be PL squared over 30 EI. And then that 2x2 is going to be 4, -1, -1, and 4 times theta 1L and theta 2L. And that's equal to the right-hand side of zeros. So this expression is K minus lambda times L times delta is equal to 0. And if we define lambda as PL squared over 30EI, then we can rewrite this as 4 minus 4 lambda in the first entry, and then second row, first column is 2 plus lambda, and then the second column is 2 plus lambda and 4 minus 4 lambda. All right, so that's a little bit simpler because it reduces it to just one matrix. And then we can readily solve or obtain the equation we need for the solution. And as you may recall from differential equations, the eigensolution will only exist if the determinant of this matrix is equal to 0. So setting the determinant of that equal to 0, I'm going to rewrite it, you don't have to. That leads us to 15 lambda squared minus 36 lambda plus 12 is equal to 0. The roots of that expression, first one is 0.4 and the second one is 2.0. So the lowest eigenvalue of 0.4, that represents the lowest value, right, or it's related to the lowest value of P that will cause buckling, since lambda and P are directly related, right? So I'll note here, this is the lowest value to cause buckling. So looking at that lowest value, that means PL squared over 30EI, which is what we defined as lambda, is equal to 0.4. So that means our first critical buckling load is equal to 12EI over L squared. All right, so that represents the finite element solution using just one element. Let's compare that to what we know to be the exact solution for a simply supported beam with axial load only. The exact solution, which we found in the last lecture, is pi squared EI over L squared. Right, and I'm using the lowercase l here because that's what we're using for the element length. In this case, right, the full beam length is equal to the element length. So this comes to, in numbers, 9.87 EI over L squared. So with just one element, we get about 21% error. right? So that's not good enough. That's too much error. So we need to refine the solution, and we can do that by increasing the number of elements. All right. So with 2 elements, I'm not going to go through the whole thing. We'll just outline the steps. All right, so you would first start with this equation, right, the 4x4s, 1 for each element, right? And you would not be eliminating all of those columns yet because the boundary conditions are going to be spread out over 2 elements instead of applying to the single element. So start with the 4x4, apply it to each element, and then you would overlay those matrices. So overlay the element K and L matrices. All right, so you would have a 6x6 for 2 elements, and then impose boundary conditions. And after imposing the boundary conditions, you would obtain a 4x4 first partition. Solving that determinant equal to 0, you would get 4 roots. That would be, the first one is 0.0829. Second one, 0.40. The third one, 1.073. And the fourth one, 2.0. So as a gut check, right, it makes sense that 2 of our eigenvalues, oh, not that one, these 2 eigenvalues match with the 2 eigenvalues from our first solution, right? But we have 2 others to inform our results. So here, now we have, since we have 2 elements, 1 element length is equal to half of the beam length. So taking the smallest root and solving for the critical buckling load, we have PL squared over 30 EI for lambda is equal to 0.0829. So our critical buckling load comes to 2.487 EI over the element length, little l squared. But since we want to compare it to our equation that includes the whole beam length, we're going to make that substitution of small l is equal to big L over 2, and that brings us to 9.948 EI over capital L squared. And this one is within 1% error. So as you can see, this solution very quickly converges, and with only 2 elements, we have a sufficient solution, right? So as I mentioned last time, right, when we found the constant C1, I think is what we were left with, and then we found the eigenvalues and eigenvectors. The magnitude of that constant is not important to us, and so that's what this note here is speaking to. The absolute magnitude of these buckled shapes is not going to be found using these solutions, and that's okay because all we really need is the relative shape. So what we do is we normalize these mode shapes or buckled shapes and just plot them. And so what we'll do is just set one of the displacement values equal to 1 and solve for the rest. Common practice and my preference to normalize it so that the largest displacement is equal to 1 in your deflected shape, but you don't necessarily have to do it that way. So the first shape is, we'll say normalizing with respect to the rotation, all right, on one end. And so if we say that theta 1L is equal to 1, and that's using our first eigenvalue, then the results that we would obtain for the remaining displacements are shown here. So plotting that, all right, and we'll use the sign convention of positive deflection upward and positive rotation counterclockwise to interpret these results. We have a positive slope at node 1, 0 displacement at the boundary conditions, right? And then at node 2, we have a slope of -1. So that's just in the opposite direction, same magnitude. So our deflected shape is like this, where we have a positive value for V2 and a slope at node 2 of 0. For the second mode shape, the eigenvalue is 0.4, and the critical buckling load associated with that is 48 EI over L squared. And so comparing that to the exact solution, that would be consistent with 4 pi squared EI over L squared, which is 39.51 EI over L squared. So not as good of a solution for the second mode shape, right? But we'll go ahead and plot those results. Again, setting the theta 1L equal to 1. And then this time I'm going to, just for the sake of demonstrating that you can, interpret the results according to a different sign convention. So when it comes to interpreting results for these deflected shapes, it doesn't matter which sign convention you use because it's all relative, values and signs, all relative. So applying a different sign convention, we can sketch it like this. So we would have a positive slope at node 1, a negative slope at node 2, and a positive slope at node 3. Displacement of 0 at node 2, and then connecting those conditions, we would end up with a deflected shape that's something like that. So we'd have our theta 1 is equal to 1 over L, theta 3 negative 1 over L, or no, positive 1 over L, theta 2 is negative 1 over L. Questions so far? Okay. So on the next page, there's another example here. This is a beam that has a fixed end at node 1, and at node 3, you have a roller support that will prevent vertical displacement, but you have the applied axial load at that end. So it's free to rotate and deflect axially at node 3. Node 2 is unrestrained, and we have a 2-element setup. Boundary conditions come from the supports, right? 0 slope and displacement at node 1, and then 0 displacement in the transverse direction at node 3. So with 3 boundary conditions, our overlaid matrix equation, the 6x6, will reduce to a 3x3. And so we would solve this using MATLAB, for example, which that solution is provided on the next page, and I'll break that down for you guys in a moment. And we can obtain our 3 roots, all right? So when we solve for the determinant of that being equal to 0, we get 3 roots from a cubic equation for lambda. The lowest eigenvalue comes out to 0.1726, right? So I'll note here, this is your lowest lambda. And then solving for the critical buckling load, we get 20.7 times EI over L squared. Comparing that to the exact solution for this particular set of boundary conditions is 20.2, so that's a pretty close solution. And then our mode shape that corresponds to that first buckled mode is shown right here, right? So this is the non-zero displacements and rotations. If we normalize that, all right, we could set the maximum value equal to 1, which would be the rotation at node 3 times L, and then that would make the others negative 0.328 for theta 2L and negative 0.474 for V2. All right, so that's just taking this and dividing it by theta 3L. And then interpreting the results, right? Of course, we have 0 slope and displacement at the fixed end, 0 displacement at the right end, and then a negative displacement value at node 2, a negative slope at node 2, and then a positive slope at node 3. And you can also sketch it this way and interpret the results with the reverse signs. So then another example is crammed down at the bottom of this page here. We have a column that is clamped at both ends. So one end resists axial displacement, the other end does not, but both are clamped against rotation, right? So no rotation, no vertical displacement at either end. So this adds one more boundary condition to our problem, and it would eliminate the third column in this matrix and the third the third column and third row in these matrices. So your first partition would be these 2 by 2 segments. And then you would end up with, if you have a 2-element model, right? And so if you have a 2-element model, that would mean that your element length is equal to half of the beam length. All right, so then you would have these two results there from the 2 by 2. So the critical buckling load, you would obtain 40 EI over L squared compared to 39.5 for the exact solution, is pretty good. And if you refine that further to a 4-element model, that means the element length is equal to 1/4 of the beam length. Then your lowest eigenvalue would be 0.0829. That would result in a critical buckling load of 39.8 times EI over capital L squared, which is even closer to the exact value, but not that much of a gain for the extra amount of effort, right? So it depends on the configuration, whether you need to add elements beyond 2, right? But not too hard to do in MATLAB, or if you're using that for a solution, right? Now let's see, did I note everything on here that I wanted to? I'm just going to go ahead and note, so you can have for your record, even though I said it, your boundary conditions would be V1 is 0, theta 1L is 0, V3 is 0, and theta 3L is 0. So you'd end up with 2 roots. Because those 4 boundary conditions will reduce the 6 by 6 to a 2 by 2 for the first partition.
So with like the simply supported beam we had earlier, and we had 4 roots, what would those other 2 roots be, and like how do we, I mean, I guess we know which one controls it's the lowest, but are those of any value to us?
Yeah, so they would represent the higher buckled modes, if that's what you're interested in. Yeah, there would be an inflection in there, yeah. Okay. Usually we only care about the first buckling mode, right. But yeah, that's what those would represent. But with that solution, it's more likely that the higher modes, right, because we looked at the second one in that case, so here's that inflection there. But we also saw that the result is not as accurate, right, for the higher modes. So if you want accuracy in the higher modes, you might need to refine your solution more than you would for the first mode.
Right. Well, and if it had another mode of buckling, like if it buckled another time, but we only have 3 nodes in this thing, we wouldn't really be able to necessarily, like it'd be kind of difficult to plot what the shape is a little bit, right? That's true. So, okay, yeah, so that's a good question. So what, let's see. Yeah, so what do these represent then? I'd have to dig into that and before I give you a meaningful answer. Okay. But yeah, that's a great question. I'll look into it. I guess, do you typically need more nodes or segments if you're expecting a higher mode of buckling? Like a fixed...
Yeah, to accurately represent it, I think that's what it would come down to. Yeah, is in order to accurately represent the shape, you would just need to add elements, right? But these, would kind of give you a target for what those mode shapes are. Yeah. Yeah, good question. Any others so far? Okay. All right, so then on the next page, I've got a printout of the MATLAB code and results for the first example. So this is the 3x3 solution. All right, so we have our bending matrix, our buckling matrix here, and those are just defined here. And then this is the command that does all the work, all right, or these are the commands. And these are two different ways to obtain the solution. So I'm going to break it down and explain the difference between them. This first one, I'll mark in green, or actually I'll mark the first one in red here. So this first one represents, well, actually, first I'm going to define above. Let's just do this. So in these commands, the capital X represents the eigenvectors. And the capital D represents the eigenvalues. And those of you that are familiar with MATLAB, I'm sure you may have used these commands before in other applications. But of course, you can pick any letters you want to represent those eigenvectors and eigenvalues. It doesn't have to be X and D. So that first command represents the equation, the matrix K minus lambda times the buckling matrix is equal to 0. In this solution, right, and that is represented by this first set of results. In this solution, you would want to target the smallest eigenvector, the smallest eigenvalue to obtain the lowest critical buckling load. All right, so here D is just equal to lambda. And this would be the smallest value. And then the corresponding mode shape, or the corresponding eigenvector, would be spit out in the same column as that lowest eigenvalue. And those mode shapes, right, in this column, this represents, since our boundary conditions are not included, that represents the remaining displacements. So that would be V2, theta 2L, and theta 3L, representing the rows in the eigenvector matrix. Right? What is that doing? So here you would divide all by 0.2305 to normalize, consistent with what we did on the previous page. And that would be for normalizing so that the largest value is 1. Again, you don't have to do it that way, but that's common. All right, so that's the first way to do it. The other command, which reverses the order of the matrices within the eig command, this represents the reverse equation, or the inverse of the equation, right? So that would be the buckling matrix minus 1 over lambda times the beam bending matrix is equal to 0. So you can use either one, you just have to make sure you keep track of which one you're using and understand how to interpret the results, because you will get different output for these two commands. So if you use the second one, then you want to identify the largest eigenvalue, which would represent 1 over lambda, right, to find the lowest critical buckling load. All right, so here your eigenvalue is D. All right, and D is equal to 1 over lambda. So these results are consistent with that command. In this case, it would be this guy as our eigenvalue of interest, and these would be the corresponding values for the eigenvector, and we can normalize to plot it. I do like always normalizing them because sometimes you get really, really small numbers and it can be hard to just kind of figure out, relatively how are they with respect to each other. So normalizing it so that the largest value is 1, so any value is 1 is an easy way to do it, and also makes it a lot easier to interpret the shape, right, relative to the supports where everything's 0. All right, so I've got one final comment here, and then I will release you. So this X, right, represents, and this is summarizing a lot of what I just said, it represents the relative buckled shape, or shapes, right, which represent the unknown displacements that you're solving for in the finite element setup. So again, signs and values are all relative. You can interpret using any sign convention. So for this one, right, we would know that V1 is 0 and theta 1 is 0 due to the boundary condition. And then we would know that V2 has some magnitude, and if we assign that direction as negative, right, we have negative V2 and a negative theta 2, so negative slope. And then over at node 3, we have 0 from the boundary condition and a positive slope. All right, for a deflected shape that looks something like that, I really exaggerated the 0 slope over there. It'd be more, I don't know. I didn't give myself enough room to make this sketch well. There we go, that's a little better. All right, so you could also flip those signs for the deflected shape. Questions? Do you want to know what's coming up next? Did you take a peek in the notes? So we're gonna bring elastic foundation and beam vibration into the picture. So, yeah. But you don't have to do any of that for your final project, so.
No math,